Okay, so now, before now we talk about PAC learning already, right? Okay. Yeah, before now we talk about PAC learning already, right? So you can take a look about right here and also right here. So all the derivation, right, is the same that we have discussed. I think maybe you're familiar with this one, right? Okay. So I think later you're going to see different equality different inequality, right? For instance, for the support vector machines, right, the inequality will be much more complicated, right? But that's based on some other assumption, not like this assumption, of course, right? You know that it won't be so powerful to deal with all kinds of all kinds of problems, right? Okay. The last part we talk about VC dimension. So what is VC dimension? Later, VC dimension will be will be existing in a term here when people talk about support vector machines. Okay, I mean there will be some theoretical stuff, but here I just want to give you some introduction about this idea, right? VC dimension, you know this guy, right? Vapnik is the founder, one of the founder, could be the sole founder for the support vector machines, right? Okay. I still remember that once that he joined the interview, the job interview in NYU, where I was the PhD there, right? So he gave a talk, right? Then after the talk, a lot of people say, "Oh, that's the time, 1999." I remember, right? You were born, right? 1999. Not yet. Okay. 1990. Yeah. Some of you're still, you're not exist, right? Okay. Anyway, so yeah, so Vapnik gave a talk and he say, oh, he introduced support vector machines, right? After that, then in the end, a lot of professors asking, oh, how about this or how about that? You mentioned. I still remember like one professor mentioned about minimum description length, right? Okay, one of the strategy that can be used for machine learning, right? Okay. Anyway, yeah, and also some other things. And Vapnik always say, oh, this and that. He didn't say, but it's like all other methods like garbage also. Yeah, he's so confident about his method, right? Like this. So he mentioned a very famous quote. I still remember. So we always say, oh, there's a gap between theory and the real world, right? And real world, there's a gap, right? So when we use whatever fancy theory, we cannot use a theory to predict the real world phenomena, right? There's a gap. Could be a huge gap, right? He said, the Vapnik say, oh, your theory is not close to the real world phenomena just because your theory is not good enough. My theory is better than your theory. Yeah. So later he introduced support vector machine. At that time, support vector machine is very good to that's a useful, that's a face detection, face recognition, something, right? Like this, right? So I mean, better than many other models. Yeah. So yeah, at that time, that's for sure, right? Okay. But now we run into another page, right? So what is the VC dimension? Okay. First of all, VC dimension is to use for what? It's a measure VC H. H is what? Hypothesis space. Okay. So we use this to describe hypothesis space. Okay. Like the capacity. Capacity means what? Means this hypothesis space is like very powerful or less powerful. Okay. So VC dimension is high means that okay, this hypothesis space is very powerful. Okay. So then here comes the very long sentence. could be very hard to introduce, okay, to do this to explain. So basically, we say the hypothesis space, okay, they'll be powerful enough so that we can shatter endpoints. What do you mean by shatter? Shatter means that, okay, where is the shatter means that we can solve these endpoints. We can solve these endpoints. Okay. Where's the example? Shatter means we can deal with this endpoint. What do I mean deal with? Deal with means that for these endpoints, we may have all kinds of labeling, right? Right. For instance, yeah, I better to use the. Okay. For instance, we say, okay, if there are 3 data points, right? Okay. Oh, we can say, oh, maybe 2 of them positive, right? So 1 of them is like negative, right? Okay, that's one kind of labeling, right? So if for any kinds of labeling, right, right, we can predict them perfectly. We say this hypothesis shatter those points, right? Okay, so the definition is like for any labeling of those endpoints, we can find consistent hypotheses, meaning that we can classify them perfectly, right? So we say the edge, the hypothesis space, shatters those endpoints. Okay, those endpoints, right? Then what is the VC dimension? VC dimension means is that, okay, if we try the hypothesis, okay, we try to increase the data points starting from 1, 2, 3, 4, 5, okay. When we have more and more data points, right, it's getting what? Harder to be shattered, right? For instance, if we have one more data, right, like this, right, it's harder, right, to separate, right? Because maybe we are going to try what? Like, okay, like this, right? So we can separate between 2 parts, right? So when we have more and more data, right, given all kinds of labeling, right, can we shatter those points, right? It'll be harder, right? So when is the time that we say, oh, that's too many data points, I cannot deal with them? That's the end, okay? That number of data points is going to be defined as the VC dimension. Okay? Very complicated, right? Why not try some examples? Four points, right? Okay, 4 points, right? So now we are going to say 4 points, and if we try rectangle hypothesis, which is the one that we are familiar with, right? So 4 points, and we try rectangle hypothesis. So we're going to say 4 points and the rectangle hypothesis. Rectangle hypothesis can shatter 4 points. Can shatter these 4 points, right? Meaning what? Meaning that these 4 points, no matter what kind of labeling that we assign them, we can always find rectangle hypothesis and predict them, classify them perfectly. Okay? I think you can imagine that, right? Suppose, okay, this one and this one positive, right? We say, oh, rectangle, like this. And this one, if there's only one to be positive, right? Okay, rectangle right here, right? If this one and this one, then rectangle right here. You got that? So we can always use rectangle hypothesis to classify all the data points perfectly, right? No matter what kind of label assignment that you provide. Yeah? So meaning what? Oh, meaning that these 4 points is too easy, right? Compared to compared to the hypothesis space that we have. Okay? But how about 5 points? How about 5 points? Right? If we have another point right here, we are running into trouble, right? Rectangle hypothesis, not possible, right? I think, for instance, if we say, let me just make it, okay. How about like this? Right here, okay? So if we say positive and positive, not possible, right? Okay, we cannot use any rectangle to classify things, these 3 to be positive and these 2 to be negative, right? It's not possible. So 5 points, we give up. Then we are going to say, what is the VC dimension for rectangle hypothesis? We say 4. Okay, 4 is the maximum number of data points that we can deal with. Okay, so VC dimension of the rectangle hypothesis will be 4. Okay? Yep. So how about this one? Okay, if we consider interval, you know that, right? In one-dimensional space, are we going to say, I mean, what kind of VC dimension for this simple hypothesis? Imagine that the VC dimension, simple means that the VC dimension cannot be too high, right? Okay, so we start from what? 1 and 2 and 3, okay? So we're going to say VC dimension for this case is 2, because when we are given 3 data points, right, we cannot shatter them well, right? Okay, interval is not possible. Okay, 2 points will be okay, right? But 3 points is not okay, right? Given this example, right? Okay, let's come back to this definition. Okay, so I didn't say what kind of endpoints. I didn't say, right? So in fact, the definition say if for some endpoints, meaning that we are given any kinds of, just one kind of endpoints, just one kind of endpoints assignment. I mean, one kind of endpoints are located to whatever locations that we have, right? Then for any labeling, we have to emphasize any, right here, any labeling, then we can shatter. Then that's the VC dimension. Okay, which means what? Maybe you are going to say, oh, Professor, no, I think the VC dimension here is not 4, right? So can I say, oh, I draw 4 data points like this, right? Okay, like on a line, right? Maybe I'm going to draw right here. So maybe you are going to say, like, okay, 4 data points, right? On a line, right? Like this, right? I say, oh, positive and positive and negative, negative. Oh, Professor, you cannot shatter these 4 data points, right? Which is true, right? But what did I say? Some. Just one case, that's okay. So one case, if there's be 4 data points, okay, we try any kinds of 4 data points, right? If just one case, one set of 4 points, we can shatter them, then we say that's good enough. Yep. Okay, but here there'll be any, right? Any labeling. So you have to pay attention to that specific words, right? That's very important. So usually, for how many data points, we just draw on the circle like that. That'll be the easiest case that we can separate, right? Okay. So that's why we draw like a circle, right? Like a circle, right? We put it like in some random space, random locations, maybe more like a circle, so that we can easily separate them, right? Okay, you got that? Done, actually. So, I give you one example. Could be the assignment, right? Okay. So, triangle, right? What is triangle, right? Triangle can be like what? Okay, if we use triangle, right? So if these two are the positive, right? So we can use triangle. Oh, sorry, too bad. So we can use triangle to separate them, right? Easily, right? Triangle like this, right? Okay, triangle hypothesis. So do you know what is the VC dimension for triangle hypothesis? Do you know? Can you make a guess? I mean, you probably don't know now, right? Can you make a guess? I think definitely you know that 5 will be okay, right? So the result is actually greater or equal to 5, right? Do you know the answer? Triangle. What's the VC dimension for triangle hypothesis? Make a guess. Right? I mean, you probably don't have time to prove your statement, right? But make a guess. 100? No, of course not, right? Yeah, the hint is less than 10. Okay, but how much? Do you know? Anyone? Less than 10 and greater than or equal to 5, right? Okay. Anyone? You want to make it? I mean, nothing to lose, right? Probably, I mean, you don't. Yeah, the answer is 7. Yeah. Yeah. So, yeah. So the VC dimension for triangle is 7. Prove it. Okay. Prove it in your assignment, the homework one. Okay. So you can just simply draw the 7 data points, right, in a circle, right? Some kind of circle like position, the general position, usually we call that, right? So you can easily separate them. So then you draw for, I think you can just show a few examples, right? You know that you can be convinced that you can shatter those 7 points well, right? Okay, no matter what kind of labeling that we have, you just need to try one location, one set of 7 points location, right? That'll be good enough. But with all kinds of labeling. Okay? Then what? Then for A points, it's not possible. A points. The why A point is not possible. I think you know the answer, right? A points. It cannot be shattered by A point means that you need to describe what? For the A points, right? You need to say, oh, it cannot be shattered. Cannot be shattered means that if you, in fact, that the opposite, the negation for this statement should be what? For all kinds of A points, right? For some labeling, we cannot shatter, right? It's like that, right? Negation for this statement, right? So you just need to mention for some labeling, right? Then they cannot be shattered by any triangles, right? That'll be good enough. And for some, the negation means for all, right? It's not possible to illustrate all kinds of locations, right? So you probably just need to provide that for the easiest case. Easy case means that usually the data points are in a circle, right? That'll be easiest case. Even for this case, still cannot be shattered. That means for other situation, it will be harder, right? Okay? Yeah, so that's all for this part. Then, can we say a lookup table, what kind of VC dimension? Then we're going to say a lookup table has infinite VC dimension. I think you're going to say, oh, VC dimension, the higher, the better. Yes or no, right? VC dimension, the higher means that the hypothesis space is more flexible, right? Larger, right? Basically, it's like that, right? So, does that mean better, right? Then here is the thing to give you some clue, right? If we try lookup table means that whatever that we have from the original, the historical data, we use it and reply to you whatever that we memorized before, right? That's what we say lookup table, right? Okay. So what kind of VC dimension? So basically, just because it's a lookup table, right? So all kinds of, labeling, that's just in the historical data, right? Of course, we can use this lookup table for any kinds of situation, right? With what? Perfect prediction, right? Of course, right? Okay, so how many data points? Any data points will be okay, right? For any data points, we can always predict them perfectly, given this lookup table, right? Okay, so no error. But on the other hand, no generalization, no good, right? Okay, so it's kind of trade-off. It doesn't mean that the larger the better, right? Such a powerful VC dimension, powerful hypothesis with high VC dimension, but it doesn't mean that it's a very good one because there could be no generalization, right? Okay. On the other hand, you know that, let's say, between triangle hypothesis and also rectangle hypothesis, which one is harder? Triangle, right? Triangle is more complicated, right? But which one gives us more generalization? Rectangle. So there's a trade-off, right? So it doesn't mean that the more complicated model would be better, right? It could be associated with more assumptions, right? Okay, so which means that the result, let's say the power, generalization power will be weaker, right? Will be weaker. Okay. So in the end, maybe we choose a hypothesis space with not so high VC dimension. Okay. And also, what we didn't emphasize is that VC dimension is distribution free. Okay. Because we talk about all kinds of labeling, some labeling will be what we say very ugly, right? Ugly. So what does that mean? Very ugly. So if we mention, I just mentioned the rectangle hypothesis, right? Okay, it could be, for instance, okay, this kind of assignment, if we have 8 data points, right? This will be very hard to be shattered, okay? I can only give you this hint, right? Later, you probably know why I drew this one. So what I'm saying is that, okay, so this kind of data points cannot be shattered by the hypothesis easily, right? Okay? I shouldn't say too much. What kind of hypothesis? So I'm saying that this one looks like a very difficult data set to deal with, right? But it's an ugly data set. Why? Because there's no smoothness, right? Like all the neighbors, they will be associated with different labels, right? Meaning what? Meaning that if we want to draw some kind of, model could be like this, right? Like, that's what I mean, very ugly. Means that the boundary will not be so smooth, right? Okay? Yeah. So what I'm saying is that VC dimension have to deal with this kind of situation because it doesn't assume any kind of distribution, right? So if we assume it's some kind, maybe Gaussian distribution, maybe some others, right? Then maybe we're going to have the smoothness, means that whatever close by, nearby, they'll be associated with the same labels. But that's not the thing the VC dimension worries about. The VC dimension actually gives us the worst case scenario. Worst case. So worst case means that, okay, even for this set of data, right? Even for any kind of, some very ugly labeling, we still can deal with, right? That's why we say the worst case scenario, right? Okay. Usually, the word is smooth enough, right? So that we don't have to really worry about all possible labeling. Maybe we just need to worry about some small part of labeling, small subset of all labeling, which is smooth enough for us to consider in real world case, right? Okay, so which means that VC dimension, later we're going to use that give us a good bound, right? I mean, to say what could be a good hypothesis space, right? But actually, that's very like worst case scenario. It's too, what should I say? It's not that optimistic, okay? It's like thinking about a very always the worst case, right? So that's why in the real world, if using VC dimension for analysis may not be appropriate. Okay, in general, we're going to say later for supervised machine. There's a link between VC dimension and the training error and the training error and the generalization error. Okay. Yeah. So that's all for this part. Any questions? So later means that, okay, we're going to say, okay, maybe there's what we care is a generalization error, right? Okay, and there's a training error, right? Usually the training error is what? Smaller than the generalization error, right? But what we want to say is, okay, generalization error is smaller than the training error plus something, some function f, okay, related to VC dimension. Okay? Which means what? And also we want to say this function, okay, goes to 0 if what? The number of data goes to infinity. Okay? Meaning that if we have more and more and more data, the training error and prediction error should be what? It's very similar, right? I think you know that, right? If we have more and more data, right, how can we worry about, the overfitting? Not possible, right? Because we already have a lot of data, right? Given so many data, then we pay attention to those data points. There'll be what? There'll be what we should do, right? Because there'll be almost like 99% of the whole data, right? Of course, that's all, right? That's all, right? Okay? And if you still remember this one, the PAC Learning, this one is something like the difference that we can pay attention. It's gone. Right? It's also another term that when m is goes to infinity, then the whole thing become like a 0, right? Close to 0, right? Okay, so that's all. Yeah, so we finished the introduction, okay? Plus the supervised learning, And the next part is to finish the teaching tree, the some kind of variance. Okay. Then we move on to talk about, yeah. So if you check the, okay, hope that still we can see that, right? So then later we are going to talk about neural networks. Okay. Yep. So that belongs to another discipline, another assumption. Okay. Yep. Yeah. So see you next week.